All right, this is part two of the solid liquid gas, electrical conductivity. Of course, there's more than just that. I'm talking about, I was talking about the structures of the graphite and diamond forms of carbon. Those are just common things because is carbon's in everything, everything organic, everything organic. So there, there are some things that are kind of like miscellaneous information, but it's unique and it's something that we need to know about. So, all right, there was just a little bit more for me to talk about. Just about finished it in that one video. This shouldn't be too long unless I get carried away. We'll see. Um, Let me check. Okay, so I was going through. Oh, metalloids. I did not talk about that. Now, metalloids are kind of interesting, and on the chart, let's see. They're right here. Remember, if you make like a ladder in between boron, well, I could do it with a. I used to have a blue pen. You see me looking around the floor because the floor is like a giant desk for me in here. You would not want to see how. I don't have a. Uh oh, my light went out. Oh, there it's back. Hey, that was pretty good, wasn't it? Um, my. Well, anyway, the way my room is set up in here, this was. I'm glad that I have this room. My kids can be in the other room doing stuff. Oh, here it is. But I, the floor is like my desk. So anyway, I don't know how common it would be to hear this, and you really don't really have to go much into these at all. I mean, you could make a little. I'll put a little dotted line here. All right. So there's a little stairway. You know where that you've seen that before on the chart, and you should know that everything that's either right above, like boron, or right above or below the staircase, is a metalloid. Except aluminum is not. Aluminum's a metal, and then don't even worry about polonium and acetine. That one is a metal radioactive. We don't really need to deal with those two that much. But anyway, these boron, silicon, germanium, arsenic, antimony, and tellurium. Okay, those are the metalloids. Now, metalloids. This is something that I would probably say it's probably better to look through the book and read about them. But I'm going to tell you probably the basic, which you probably would need to know for most anything they would ask you. But could they ever ask a more detailed question? I'll show you what could happen about that. Okay, so metalloids, actually, some books call them semi-metals. Now, I think that's kind of a goofy name. I don't know who came up with that. But semiconductor is a word for it. And because of metalloids, we have computer chips and what's called transistor chips. What's neat is metalloids will conduct electricity, usually in just with some modifications. Like if you heat up a metalloid, it will conduct better. That's a neat idea. That whole neat concept. That's where the idea of a transistor, like a board or a chip, came from. If you've ever had your phone opened up and you see the little board in there, or an old any electronic device, like trying to think of what it could be, something that plays music. I was going to say a radio. I don't know if you've ever seen a radio. Everything's all internet now, but radio box, anything like that. You'll see like the inside's like a little chip, and now that could be made of silicon, for example. Now I'm not going to be able to tell you all the exact, correct, perfect description of this, but have you ever seen like a little board? You'll see like it could be even in like a remote control car, or the remote itself, or in the car itself. It's something, or a little toy, any toy that's electronics. You might see this kind of like little board, and all these little lines and wires and disconnects there. You just see this little thing looking like that all inside there. What in the world is that? Well, what it is, it's like the material itself. Like think about like a computer chip. The material itself, when it's cold, has no conductivity. But when you push a button, I mean, I don't know if I'm being perfect computer science on this explaining it. But when you push a button on the computer, it's like it sends this really high electrical, high temperature, as well as there's a current there at some point, at some place in that chip. We'll just say you push a button and some high temperature is there. So now, when you do that, you open up a pathway that was closed before. So you send the electricity here, boom, it conducts there. And so that can cause something to be on or off, on or off. So it's kind of like when you type in buttons or turn on a button, the power on, volume up, volume down. The chip is actually being manipulated by changing the temperature in different sections of it. You're able to cause it to conduct electricity in certain sections. I think what I'm saying is the gist of it. Not perfect. They're certainly not going to ask you that on AP, but you can know that silicon and most of the metalloids, what did I leave off? Those are the main ones, I guess, right there. Germanium. Okay. Oh, I put germanium. Well, these can conduct at high temperatures. Okay, so that's a useful thing because it becomes like an on and off switch. Well, they can also conduct electricity when you mix them with other metal or other substances. Now, they call this is a really weird word, well, a word you've heard of, but not for that, doping. If you dope a metalloid, it will conduct electricity better. Now, how do you dope a metalloid? What does that mean? This gets into something that that we don't really have to worry about on AP called molecular orbital model. But I'm going to show you a little bit of it, a little taste of it here. Besides the sea of electrons, besides that theory for metals, there's also one called the molecular orbital theory. And it kind of looks like this. I'll try and draw it. In fact, let me try and do it with silicon. So what you would do is first you'd say, you're not going to have to do this, but I'll just give you a quick little idea. Silicon goes up to 3s2, 3p2. So 1s2, 2s2, 2p6, and then 3s, and then 3p. We only care about the valence. So 3s2, and then 3p2. It looks like that. Okay, that's how one silicon atom. Now, let's imagine that another silicon atom. Now, if you have like a crystal, where I'll say silicon, 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 silicon. Remember, it's network covalent. So all of these are going to be covalently bonded to each other. They're all going to be attached, kind of like a metal would be. Just all of these silicons are in a crystal. Similar, a little bit like a metal. But here's the way they do what's called this molecular orbital model. And in college, you'll have to do this. You will see something like what I'm going to show you. But I'm just going to give you a little taste of it here. So we don't really care about the levels that are not the valence. In fact, what they normally do is they'll say the valence levels don't even matter. I mean, the kernel, the lower, like 1s, 2s, everything before it doesn't matter. But starting with the valence, let's say you have 3s2 and 1, 2, 3, 3p2. Oh, what a mess if I'm trying to draw this. It's better on paper, probably. Okay. So what happens is, I'm going to be out of space. I'm going to have to erase this. What a mess. Okay. I just realized it. 3s and 3s here. 3p and 3p here. I like to draw it this way because this is kind of like the way I like to explain it. Oh well, this is the best way you could explain, I guess. What the molecular orbital theory, MO, it says that these orbitals combine to make new orbitals. So it's a lot like the hybrid orbital system. You add an S with a S and a P. 1s and 1p orbital gives you sp, 2 sp orbitals. Okay, well here, in the molecular orbital theory, the 3s of one atom and 3s of another atom, and then another, they go on and on infinitely, but we'll just do it with 2. These combine, and they make something called a 3s sigma and a 3s sigma star. This is called a bonding orbital. That's called an anti-bonding orbital. It's kind of a weird thing. what happens is you put in 2 orbitals, you get out 2. All right, one is a little bit lower energy than what you had, and one is higher energy. You have 4 total electrons. The rule is you still have 1, 2, 3, 4. You still have 4 electrons to put in. Okay, so that goes in there, and they say, well, because there's not going to be a bond at that layer in the 3s, because if you have the same number of what's called the lower energy sigma and the same number of sigma stars, these are called anti-bonding and bonding orbitals. Don't worry too much about it. But here's what I want to get at, this part, the 3p's, and I'm going to have to go a little higher with them. Now, there are some different models of how they do this. But remember the p's, if 3 p's and 3 p's come together, they both have 2 electrons there and 2 electrons here. There's a couple of different ways you can draw this, but one way you could draw it would be to show you have 2 orbitals lower energy, well, 3 lower energy actually, and then there'll be 3 higher energy. Then maybe like 1, 2, 3 higher energy. Don't even worry about the names of those. I mean, these will be actually called pi, 3p pi, and this will be a 3p sigma. Those will be 3p pi, the way I drew it, 3p sigma. Star, these are all stars. But anyway, okay, so watch this. When they rearrange themselves, you are not going to have to draw this, but I'm going to put little lines to show like where they're going to. 1, 2, 3, 4 electrons. They're going to start at the bottom here. 1, 2, 3, 4. Now, here is all I wanted to show you in doing all of this. By the way, they call these bands. Each level where electrons can be is called a band. They also call it the molecular orbital. It's related to something called band theory. You can read more in the book if you want to know a little bit more about it. But here's the basic thing. So, if these bands are full of electrons, then we would say it would not be a very good conductor. It would not be a conductor. A good conductor would be one where, like, say if you're missing an electron here, now an electron can go side to side or shift over. Like if I put something negative in, here they can't go anywhere. Now, could they go to a higher energy? They could, but it would help to have a higher temperature. So that might be a way to think about it. At a higher temperature, that's one way to cause them to go up to a higher energy. So what I just did was I showed you a little diagram of a possible way, and there's probably other ways, and not the best way, that you could link together 2 silicons and then more in the crystal could go on and on. But the idea is that their orbitals combine. It's kind of like the metal theory. All the valence orbitals combine and they make these new orbitals. But if the orbitals are full of electrons, they're not going to be a very good conductor. But if you add electricity, add heat to them, well, now they can jump into that one, and it will work out better. Okay, now they have a place to go when electrical negativity comes. All right, so what is this thing about doping? So one way is you increase the temperature. That's one way that metalloids can do that. But let's just say that I took silicon and I mixed it and doped with arsenic. Okay, I doped it with arsenic. Well, let's see how arsenic is different than silicon. Arsenic is As, and it doesn't have just 2, it actually has 3 electrons in its valence. So now, when they combine, let's just say we have the same setup, 1, 2, 3, 4, 5, 1, 2, 3, 4. Suddenly, now look at that. Now you have an electron, you have a single electron here. Now, why would that matter? Okay, so if I did this with many other atoms, okay, an atom here, another atom here, well, the idea is this level, let's see, 2 and 1, let's go right across there. That level, I call it the 3p sigma, I'm just calling it on mine. In this band, electron, if you add energy, now remember, these are really close together. These atoms are connected, basically, atom to atom to atom. So they put a silicon here. Now, this electron could possibly move side to side. It's the same energy. It didn't go up or down, but if it were negative, it could now shoot over here. Okay? So that's one possibility. So you've created a little place where it can go. Let me think of another way to put it. Well, another way you could just simply think about it is that this one. Well, I don't know. I'll just go with it that way. So there's two types of doping. One is called a P-type and an N-type. N is a negative, adding an extra negative, and P would be positive, adding a positive whole. This would be what's called an N-type. If you doped it with arsenic, it's an N, and N stands for negative because you've added an electron, an extra electron in there into the system. Now having that extra electron, kind of an odd number, kind of takes things off balance, and so you can. There's somewhere for it to go back and forth. A positive one, a P-type, would be adding something like, let's see, arsenic. If I added something like gallium, and it doesn't have to be, this is not a metalloid, but gallium has only one valence electron, so it has one less electron. So now what we do is, all right, 1, 2, 3 is all we have, so 1, 2, 3. Now by adding gallium, we call that a P-type doping, or semiconductor, P-type semiconductor. And what we've done is we've made a positive whole. And what we mean by that is, notice this. When I put them in, suddenly there's a little place here where there was an electron, but now there's not because gallium is taking its place. So imagine all of these are silicons, and you have this one little gallium stuck in here. Well, now you created a positive whole. So that means that if I added negative charge, something can jump into that level. It can move side to side. It can move over from there to there to there to there and so forth. All right, I know this might sound very bizarre and weird, but you can read more about N-type and P-type. When we're reviewing for APs, one thing I'll do is I'll show you some old AP exams, and you'll go through them. And when you do that, you'll realize you'll see some questions about this at some point. There'll be some N-type, P-type, and hopefully you'll figure that out. But if an atom, I mean, here's a real simple way to put it. Like I was showing you. Say you take a metalloid like silicon. If I added a phosphorus in there, phosphorus has one more electron. So that would be, you're adding an extra negative. That's an extra electron, that's an extra negative. That's an N-type, a negative type doping. If you add an atom with one less electron, like aluminum even, then you're adding you're deficient of an electron, so we'll say you have a positive whole. Okay, so that might sound strange to you, but that's probably the most basic thing to remember for N-type and P-type. You're making, remember, mobile charge carrier. You're making a place where electrons can be mobile to, or you're putting an extra charge carrier in there. Extra electrons added in there in an N-type, and a P-type you're adding an extra place, a hole where another electron can move into. So both of those help conduct electricity. I did not do justice. I mean, great. That would not be a good college lesson on that. You have to go. I would go through. I used to teach through the whole molecular orbital theory and showing you that, and then this will make a lot more sense to you. But this is kind of how I just wanted to show you. But the bottom line is what I just told you there at the end about doping it with something with one more electron, being a negative type conduction or negative type doping, or with one less electron in its valence. So it would have, and it could have two more electrons or two less, but usually it's just one atom right next to it. Okay, so is there anything else? There's a last section on here on non-electrolyte versus electrolyte solutions. And I don't think that this is a big no. Oh, let me think about this for a minute. You know what? This kind of relates to another chapter that we're not even going to really even have to teach. But I'll just tell you this one last little bit. So let's just say that I have 1 liter of water, and in it I have dissolved 1 mole of sugar. C12H22O11. Well, first of all, sugar is what's called a non-electrolyte. So before I say non, remember, what is an electrolyte? If anything that you add it to water and it dissociates into positive and negative ions in the water, it will conduct electricity. So any strong acid and any ionic compound, you put it in water, it makes positive, negative ions, or for acids, it makes H plus and negative ions. Even weak acids would be a weak but electrolyte. Those are electrolytes. What if you put something in water and it does not dissolve into positive or negative, but it does dissolve? That's called a non-electrolyte. Now, a way to prove that, sugar. You know sugar dissolves in water, but sugar does not have any ions on that. Okay, so it's a polar molecule. It will dissolve in water. Vitamin say vitamin C, but I better not say that because now we might be getting into a weak acid there. But let's just talk about this one. So a non-electrolyte, something you put it in water, it will dissolve, but it won't conduct electricity. That's a non-electrolyte. So if I put 1 mole of sugar in 1 liter of H2O, then the molarity would be, remember, molarity is mole per liter. 1 mole for 1 liter, it will be 1 molar. All right, that 1 molar, the electrolyte. Oh, no, non-electrolyte. Non-electrolyte. Sorry about that. But now, if I put 1 liter, if I dissolved 1 mole of NaCl, well, how many moles of electrolyte will I get? I'm actually going to be putting in there Na plus and Cl negative. I'm putting in 1 mole of NaCl means a mole of Na and a plus 1 mole of Cl negative. So I'm actually going to have 2 mole of electrolyte particles. So 2 molar for particles, that's only 1 molar of non-electrolyte particles there. What if I had, AlCl3? Well, I have 1, 2, 3 negatives and 1 positive. That's 4 moles of electrolyte. So that would just tell you, all this would tell you is that aluminum chloride dissolving in water, you'd expect it aluminum ion and 3 negative chloride ions. That's 1, 2, 3. That's 4 molar of electrolyte. You'd expect that to be a better conductor of electricity than just NaCl. That only has 1 and 1. 1 sodium and 1 chloride. So having more particles per mole, AlCl3 or NaCl would be a better conductor of electricity. But then non-electrolyte would not conduct it at all. Okay, so that's by the way, that number, the number of dissolved particles, is a symbol. It's an italicized letter I. The I number. And it's something for if the solute's I number, I value, tells you how many particles dissolve from every molecule that you put in. And that has a significance in chapter 11. But we're in chapter 10, and the next chapter we're going to go to is chapter 12. We're not even going to do 11 because they took that off. That's not a focus on the AP anymore, but it will be something that you'll see later on. And I had that in my notes here, and I just kind of wanted to tell you about that as well. And what I told you, the summary is right there at the end. An electrolyte like sodium chloride dissolved in water, and you get 2 moles of dissolved solute. But a non-electrolyte, 1 mole of solid, like sugar, dissolving in water gives you 1 mole of aqueous sugar. Okay, well, that's all I'm going to say. And answer those questions, as I told you earlier, number 1, 2, 3. And then there are other questions on there. There's some neat stuff in there, but there's some other questions that we will look at. You'll see the answer key, and we might talk about them in class. But chapter 10 has so much interesting and factual information, and I'm just focusing on the main ones they're going to be talking about and dealing with AP. So I'll see you guys later on.